Okay, here is another solids of revolution example. And here we have the region bounded by y equals x, and y equals 1/3 x squared is revolved about the line x equals -1. We want to find an integral that can be used to compute the volume of the resulting solid. Here we have a graph of three things here. The line x equals -1 that we're going to revolve about, as well as the region bounded on the one side here by the line y equals x for x from 0 to 3, and in blue the parabola y equals 1/3 x squared from x equals 0 to 3. So we're revolving this bounded region here about this line. So we get an interesting object here. And we can approximate the volume of this solid using washers. So here's what it looks like for 4 washers. And of course, to get a better approximation to the volume, if we use more washers. So here I have this for 11 washers. And here is another view, this one from a little bit below the solid. And here is a cutaway version. Okay, so we're going to have to figure out the volume of each of these washers, but it's really not bad. Here I have an illustration of the ith washer. I here is just a subscript. So in previous illustration or animation, we had 11 washers. That means I would start from 1 and go up to 11. So here I have an illustration of my ith washer, and notice it's around the line x equals -1. And what we want to do is figure out this volume of this washer in terms of its surface area, well, not surface, its cross-sectional area times its thickness. So my cross-sectional area, I have the difference between two areas, one area for a circle of radius capital R sub I, and another area for the circle of radius little r sub I. So I have these pi capital R sub I squared minus pi little r sub I squared, and the thickness is change in y. So you can see how this is working out. Okay, here we want to consider the outer radius of this washer, and notice that it's going to be the distance from the line x equals -1 here on the left, that vertical line, to the line through the point on the parabola. And so if my x-coordinate here, my x sub I, is going from the y-axis to that point on the parabola, then my overall outer radius is 1 plus that x sub I. Now the parabola I can write as y sub I is 1/3 x sub I squared, or I can solve it for x in terms of y and have x sub I square root 3y sub I. But here we really want to use the x sub I is square root of 3y sub I because that's x in terms of y, and y is our variable of integration. So our outer radius is in fact our capital R sub I is 1 plus square root 3 times y sub I. Now we want to do a similar thing for the inner radius. So again, my inner radius will be 1 plus my x sub I. But now we're on this line y equals x for the inner radius. So our r sub I is 1 plus y sub I. And again, we want our r sub I in terms of y sub I, as y is the variable of integration. So notice that again, 1 here is going from x equals -1 to the y-axis, and my x sub I is distance from the y-axis to the x-coordinate of the point on the line. Okay, so now we can write that our volume for the ith disk in terms of y sub I is this pi 1 plus square root of 3y sub I, that quantity squared, minus pi 1 plus y sub I, that quantity squared, all of that times a change in y. So this will give us a method of estimating the overall volume. So if I have 11 disks, then I would have V1 plus V2 and so on up to V sub 11. Now I can write this in sigma notation as shown. Notice that we have our y sub i's here and a change in y here. And what we can do then is take Riemann sums. And from our Riemann sums, in the limit, we're going to pass to a definite integral. And you have to recall x was going from 0 to 3, but y was also going from 0 to 3. And here, since we're integrating with respect to y, that's the 0 and 3 that I used. Notice the y sub I is now replaced by y, and the change in y corresponds to the dy, the differential of y. And then to finish this problem, what you can do is multiply these things out and just use the power rule and the fundamental theorem of calculus to get an actual final answer. That's that. Thank you.